Today we're going to review property of exponents. Exponents have to do with like multiplication. Division is considered multiplication or the inverse of multiplication. So exponents deal with repeated addition, which is multiplication, or repeated multiplication. And there are a couple of rules here. All of them you've sort of seen before, maybe in Math 1, maybe in Math 2. Rationals may be new to you, so that's where our exponents look like fractions. But I'm going to go ahead and review all of these and show you the shortcut and show you the long way to do this. In my opinion, the long way is the easier way. It takes a little bit of extra time, but you make less mistakes that way. So the first one we're going to talk about is our product of powers. This is when you have something that has an exponent and it's being multiplied to something else that has the exponent. The big thing to remember is that product of powers deals with values that have the same base. So here base just means b. So you had some number to the exponent times the same number to a different exponent. What we like to say is that you add your exponents. Now this is a shortcut. There are a lot of rules to memorize, but if you can understand kind of where they come from, then you don't have to necessarily memorize the rules. You just have to be able to kind of see how this functions. So for example, I have 2 squared times 2 to the third. So if you look, they have the same base. The base is 2. They have different exponents, 2 and 3. Well, the shortcut says, hey, if you just add those exponents, 2 plus 3, then you end up with 2 to the 5th power. Again, some people are going to be able to recognize that very quickly, memorize it, and kind of move on. But memorizing doesn't help if you don't know what it means. So an exponent means repeated multiplication. So something times something times something times something. So if I look at 2 squared, this is not always just 2 times the exponent. It means that the base 2 will show up twice. So 2 squared can be written as 2 times 2. Then I have another multiplication, so quantity times a quantity. 2 to the third can be written as 2 that shows up 3 times. Oops. 2 that shows up 3 times. So you have your first group, 2 squared and 2 cubed. Well, because you have all multiplication, what you're saying is the number 2 has been multiplied by itself a grand total of 5 times, which is where that shortcut comes in. You had 2 of them, then you multiplied by another 3 of them. So in total, you multiplied 2 5 times. 2 times 2 times 2 times 2 times 2. If we look at one that involves variables, we want to make sure first off, do they have the same base? Or are they the same variable? Are they the same number? Yes. So x squared can be written as x times x. X shows up 2 times. And those 2 x's are being multiplied by 5 additional ones. So 1, 2, 3, 4, 5. Well, in total, I have complete and total multiplication. So in total, I have 1, 2, 3, 4, 5, 6, 7 of them. So my answer is x to the 7th. That's where the shortcut, if I add these 2 together, I get 7. I don't care which way you do it. I prefer the long way. I really love the long way because instead of having to memorize just rule after rule after rule after rule, we kind of see how things function and play to what we already know. So that's what we call a product property or product of a power. Power is just another word for exponent. So a power of a power means that I have exponents that are being raised to another exponent. So for example, if we look at here, we have your base that showed up m amount of times, and we're going to write that down n amount of times. So what the shortcut says is that you're going to multiply your exponents. And again, these rules don't make sense if you don't understand where they come from. So for example, 2 squared raised to the 3rd power. So I start with my base, and I see that it has an exponent of 2. But this whole group of stuffs, could be anything, that whole group must show up a grand total of 3 times. So if we write it out long, then it says that 2 squared shows up 3 times. That whole group of 2's. And if we keep breaking it down, well, 2 squared just means 2 times 2, times another 2 squared, which means 2 times 2, and another 2 squared means 2 times 2. All of that is the same multiplication, so we can just count them. 1, 2, 3, 4, 5, 6. So when you kind of see it all written out, then you can understand why the rule works that it does. 2 3 times gives you a total of 6. We had 2 written out 6 times. So again, let's look at one that includes a variable. I have a group of things, in this case y cubed, that has to be written down 7 times. So y cubed, y cubed, so I have my group written down 7 times. If you needed to go through and break each one of these y cubes down, you could. So you can see that there are 1, 2, 3, 4, 5, 6, 7 different sets of y cubed. Then you can go through and you can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and you end up with 21. Or I would have said 3 plus 3 plus 3, all of those added together, and you end up with a value of 21. So its exponents just mean the same thing shows up over and over and over again. The same is true with a different kind of form of power of a product, and that is when you have multiple parts in your group. In that case, we're going to distribute your exponents. Again, I really like just doing a little bit of longer work that makes sense. So, for example, if I have a base, this base includes 2 different pieces, A and B. Those could be numbers, they could be letters, and an exponent. Then what we're going to want to do is distribute that exponent into each part I'm looking at. In this case, we can see that we have a base of 2x, so a 2 and an x and an exponent of 3. The shortcut says that both the 2 and the x receive the cube. A lot of students make mistakes at this particular question. That's why I like doing a little bit longer math. So what I'm seeing as this entire group will show up 3 separate times. So 2x, x, and 2x. Because they're all being multiplied, now I can just say 2 times 2 is 4, times 2 is 8, and x shows up 3 times. It's a little bit more writing, but it's not a whole lot more work. In fact, the work itself is a little easier because you can just remember that exponent means over and over and over and over again. So look at what happens when we have one that involves letters. Again, I have a group of items, and that group must show up 2 times. So 3xy must be shown twice, and the operation that I keep talking about is that multiplication over and over and over. Well, now you can just multiply like terms. 3 times 3 gives you 9. X shows up twice, y shows up twice, therefore your product is 9x squared y squared. If all of those work with multiplication, then their opposites work for division. So quotient is just a fancy word for division, so the division of power. The shortcut is to subtract. So if we look and we kind of use some of that vocabulary that we've done before, inverse means opposite. So if product means multiply, division means divide. If I added before, I now have to subtract. So there's that concept of inverse. So again, I have the same base in my numerator and my denominator with different exponents. The rule says I'm going to subtract. If you're doing it long ways, it kind of looks something like this. I'm going to use the easier rules and just set it up with the fraction. So here's my fraction bar. That's a little crooked. In my numerator, I will have to write the number 2 8 times. In my denominator, I will have to write the number 2 5 times. The reason I like this method is because if I look at these pairs, 2 divided by 2 is just the value 1. What we used to say, or what we say a lot, is that they like, ooh, I've written too many 2's. There we go, 1, 2, 3, 4, 5. Yep. So if I look at this first set, this second set, then 2 divided by 2 is just 1. So we say, hey, these cancel each other out. So I don't have to deal with subtraction just in case I'm dealing with extra negatives and whatnot. So when I do it like this, I say, okay, well, I have 3 2's up top, nothing left in the bottom. So all fractions with nothing in the bottom can have a 1. And 2 times 2 times 2 gives me a value of 8. So I don't have to worry about, oh, are there 3 in the numerator? Are there 3 left in the denominator? What happens if I have a negative? It's extra math. So again, let's look at what happens when we have variables. I have the same base. I have different exponents. And I'm just going to extend or expand that fraction bar. So there will be 11 t's in the numerator. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 t's in the numerator and 5 t's in the denominator. And for every 1 t in the numerator, we'll cancel with 1 t in the denominator. So they cancel out top and bottom. And this tells me that I have 1, 2, 3, 4, 5, 6 t's left. Nothing down here. So, you can fill a hole with a 1. So you have t to the 6th. That's what this fraction reduces down to. And if you look, 11 minus 5 gives you the value 6. But again, I like doing it a little bit longer, makes less math. Power of a quotient. Okay, that just, power again means lots of multiplication. Quotient means with a division sign that I'm looking at. So power of a quotient, if we distributed before, we're going to still distribute. Notice that this time, instead of having one base, I had a fraction. Now, fractions are not scary. And I had a fraction that was raised to a power, and that power went to each one. If we use the longer method, we kind of avoid that. So 2/3 raised to the second power, or 2/3 squared. What I'm seeing is a group of stuffs raised to an exponent. So 2/3 will need to show up twice, and then we multiply fractions straight across. So 2 times 2 gives me 4, and 3 times 3 gives me 9. We ended up with the same answer, and we didn't even use the rule. But you can see it did get distributed. You can see that 2 squared here and that 3 squared here. Sometimes, like I said, those rules can get a little overwhelming, so I just like writing things out. So if we look at this one, 6/7 squared, that means that I have a group of stuff. Doesn't matter what that stuff is, numbers, letters, fractions, decimals. That stuff needs to be written down, in this case, 2 times. So if we multiply straight across, 6 times 6 is 36, 7 times 7 is 49, and so my fraction is 36 over 49. So these first 1, 2, 3, 4, 5 rules up to this point are all mathy things. So the top half is math. The bottom half is what I call location. There's no math, it's just that things get moved around. All right? 0 exponent rule. My personal favorite. Anything raised to the power of 0, anything at all raised to the power of 0 is always going to be the number 1. Is always, always, always the number 1. So anything, it does not matter if it's 0 to the power of 1, it doesn't matter if it's 1 to the power of 0, it doesn't matter if it's 6 to the power of 0, 428.6935221 squared, quantity raised to the power of 0. Anything raised to the power of 0 will always be the number 1. So 2 to the power of 0, always the number 1. A group of stuff, we got a group here. The whole group raised to the power of 0, the whole group will have a value of 1. And again, it can look nasty. It can look like 0.6371 x to the 1/3 y to the happy face z raised to the power of star. If that whole group is raised to the power of 0, the answer is 1. Always. The one that students mess up on a lot or kind of get scared about is a negative exponent. A negative exponent is all about location in a fraction. So a fraction has 2 parts. It has the numerator and the denominator. If the exponent is negative in the numerator, we move the whole thing down to the denominator. If you have a negative exponent in the denominator, we move it up to the numerator. So you can see here, we had a base, and that base had a negative exponent. Well, right now, I'm not looking at a fraction, but I do know that I can turn anything into a fraction by putting it over the number 1. So whenever I see that negative exponent, it literally takes it from the top of my fraction, anything that it's attached to, not the whole thing, just anything it's attached to, will slide down into the denominator or into the opposite spot. If it was negative in the bottom, it moves up top. And if it's negative in the top, it moves down to the bottom. So for example, 2 to the negative 3rd, I have a base of 2. an exponent of negative 3. Right now I'm not looking at a fraction, so I can make anything a fraction by putting it over the number 1. Well, my negative exponent says, hey, this sucker is negative up top, so we're going to move it down to the bottom. And when you do, notice what happens to that negative 3. It all of a sudden becomes positive. So negatives don't have anything to do with math. All they have to do with is location, location, location. 2 to the third is 2 times 2 times 2, which gives you a value of 8. Since the 8 was in the bottom, it stays in the bottom 1/8. If I was to look at 3 to the negative 4, I have a base of 3. My exponent is negative. So right now I have no fraction, so I can put all of this over 1. Well, if you look, your negative 4 is attached to the 3, so that is the item that will move spots. It was negative up top, so when I move it, it becomes positive in the bottom. I have a hole because there's nothing else left in the numerator. Every hole that you have in a fraction gets filled with the number 1. So my answer is 1 divided by 3 to the 4th. 3 to the 4th is just 4 3s. Well, 3 times 3 is 9. 3 times 3 is 9. So that gives me a value of 81. Those 3's were in the denominator, so the 81 stays in the denominator as well. And this last one, rational exponents. These are fraction exponents. Now I know a lot of students freak out about fractions. Fractions are not awful things. In this case, an exponent that involves a fraction, all we need to do is convert it to a radical. Now a radical has to do with like the square root sign. So you have a base. Now, of all the things, I really want you to just pay attention to the denominator. That is the only one that will move. Notice it is low, so it's going to move up high when we turn it into a radical. So the denominator was an r, but look what sits on the shelf of your radical. Everything else stays the same. Everything. Nothing else moves. Nothing else touches. So if I look at this example, 27 times 2/3, or to raise to the power of 2/3, all I'm going to focus on is what's causing the problem. That's the 3, that denominator. So whenever I have to convert it to a radical, well, 27 squared is not causing a problem. It's that 3. So notice where that 3 just bloop, sits on the shelf. And now I'm dealing with the cube root 27 squared. And that's it. Then you can pop this sucker right in Desmos. It'll give you an answer. So if I was looking at 8 to the 1/3, 8 to the power of 1/3. Well, the thing that's causing the problem is this 3 in the denominator. So when I go to convert it, the 3 comes out of the denominator, sits on the shelf. Now I've got the cube root of 8, and from here I can use a calculator or Desmos to get those numbers. So what I'm going to have you do is practice using all of those rules individually and then using them in combination.